In the last video, we talked about the method for solving linear first-order differential equations with what is called an integrating factor. And with the integrating factor, you can multiply through your equation, make it resemble the product rule, and then simplify your differential equation into this derivative of a product of your integrating factor and your function equal to something, and solve. In this video, we're going to do some example problems regarding this. And let's scroll down, I suppose, and get on it then. Okay, actually we don't have any space on the bottom, so we're going to scroll up. It's exciting. All right. So, again, this is from my textbook. So this is going to be section 2.3 now, linear equations. Let's start with question 8. Question 8, just going to start simple. Question 8 asks to obtain the general solution to dy dx equals y divided by x plus 2x plus 1. Now, at first glance, is this even a linear differential equation? Well, let's try to see if we can get it into the linear differential equation form, and if we can, okay, then it's a linear differential equation, and we can solve it with our method. So, if we subtract y divided by x, we get that dy dx minus, and now we can write this as a function of x, 1 divided by x times y equals this pure function of x, 2x plus 1. So we have our y prime with coefficient of 1. Okay, that's good. Check. Then we have a function purely of x times y. All right, check. Equaling a function purely of x. All right. We have all of our checks. This is indeed a linear first-order differential equation. And because of that, we can use our method of integrating factors to solve it. So, again, without recalling any formulas, let's see what we might be able to do to get this into our product rule form. What we know is that we want this to resemble the product rule. So we want this to be some mu of x times dy dx, which I'm going to write now as y prime, minus mu of x times 1 over x times y. We want this to equal, I guess let's write it like this, equal the derivative with respect to x of mu of x times y of x. All right, perfect. Well, we know that we already have the mu of x y prime here. This term is already all good. This term looks good on this y part, but we need the mu of x times 1 over x part to be good. We need this to equal mu prime. And if we go through with that, I won't follow through with the algebra, but we can remember that we have then solving that separable differential equation, which we did in the last video. So if you're not sure what I'm talking about, probably check out the last video. We have that mu of x equals e to the integral of our function of x here, which is negative 1 over x dx. All right, perfect. And again, times some constant doesn't matter, so we'll just choose 1 because it is the simplest. If mu of x equals this, let's solve this. This is going to be e. Well, this integral here, we can factor out the negative 1, so we get negative times the integral of 1 over x. We know that is the natural log of the absolute value of x. Again, plus these, they don't matter here. So this e to the negative natural log of x, we can say this is the same as negative 1 times the natural log of the absolute value of x, which using the logarithm properties, we can pull into the logarithm as natural log of x to the absolute value of x to the power of negative 1. And now e to the natural log of anything, that is just the anything. So we have x to the negative 1 is what our integrating factor is, which is kind of nice. Like when you see the expression e to the integral of p of x dx, sometimes it looks incredibly daunting. Like, whoa, what is that? But it's good to see that sometimes the integrating factor is actually just a fairly simple expression, like here, 1 divided by x. Alright, well let's actually multiply 1 divided by x through our equation and see what we get. Okay, so when we multiply it by dy dx, we get that, so let's switch colors one more time, 1 over x, which is again just x to the negative 1, times y prime, minus, and then 1 over x times 1 over x is 1 over x squared times y equals, and again, we have to remember we're multiplying mu of x through the entire equation. If we only multiplied it through the left-hand side, it would be wrong because we would be changing our differential equation. So you have to also multiply 1 over x through the second side, so we get 1 over x times 2x plus 1, which we could simplify this down, just distribute things through. So 2x divided by x just becomes 2. 1 divided by x becomes 1 divided by x. It's incredible, right? Okay. And now, as we can see, we have our product rule form, and it's all set up. So we can just say this is the same thing as the derivative with respect to x of the integrating factor, 1 divided by x, times y. And this is equaling 2 plus 1 over x. Now, this right here, when you have your equation in product rule form, this is a really nice time to go back and check, okay, did I integrate for my integrating factor? Is my integrating factor correct? Because it's fairly simple to take this derivative, and if you get back to what you have up here, you know your job is done right. So let's just quickly take the derivative of this and see if we get back. So if we take the derivative of this, let's see if we'll get to this. All right, let's do it. So first we want to take the derivative of our first function. So the derivative of x to the negative 1, or 1 over x, is negative 1 over x squared. And that's just going to be times y. And we're going to add to that, not taking the derivative of this function, 1 divided by x, but then taking the derivative of y, so y prime. And what we'll notice is that this here, this equals this. We may have reversed the order here, but we have a 1 divided by x times a y prime term, and we have a negative 1 divided by x squared times a y term. So we did it. They're equal. That means we solve for our integrating factor correctly, and we're good to go to solve the rest of our equation. So let's move this forward. What this means is if we take the integral of the left side and the right side, we'll get what we want. So integral here and the integral here. So if you take the integral of the left side, fundamental theorem of calculus, integral of derivative, they both just disappear because they're inverse operations. What we're left with is 1 over x times y. This is equal to the integral of 2 plus 1 over x, and really we could say this is all dx also. So we're going to get the integral of 2 with respect to x is 2x. The integral of 1 over x with respect to x is the natural log of the absolute value of x. And we have to, of course, remember that we're adding a constant, which, just in case we have to change it around, I'm going to say is c1. And this is our completed right-hand side of the equation. Now, just to get this left side in terms of only y, we can multiply through by x, and it's nice. It looks like we are getting here an explicit solution for y. What we're going to get is, finally, that, let's do it in a really nice color, blue, how about, y equals, multiply through by x, we get 2x squared plus x times the natural log of the absolute value of x plus x times c1. And this is our solution to the differential equation that we had. Now, if you wanted to go back and differentiate this, verify, good, it's a good exercise. This, if I haven't made any careless mistakes, though, it should be correct, which is good. So let's have fun, let's box it, and then I have another series of videos that I did on another example of linear differential equations where you have what's called a mixing problem. So if you want some more practice, you can look at that. It's where you have a tank of water, and that tank has both an entrance and an exit. So that entrance might be a leak or something, who knows. So you have a tank of water, you have some water that is coming in, You have the water level, you have some water that's going out, maybe because the water level is above that. And this problem is interesting because then you can measure how much of a certain substance is in the water. Anyway, I have another series of videos on that if you want to watch it for more practice with linear differential equations. But in the next video, we're going to talk about the final type of the final type of first order differential equation that we can solve analytically, and that is the exact first order differential equation. Ooh, not every differential equation is linear. Alright, I'll see you then.